There is something out there pulling us, not quickly, not dramatically, but inexorably. Our entire galaxy, the Milky Way, along with hundreds of thousands of other galaxies spanning hundreds of millions of light years, is being drawn toward a single point in space. We're moving at 600 kilometers per second. That's over 2 million kilometers per hour, fast enough to cross the distance from Earth to the Moon in about 38 minutes. And we've been moving at this speed for billions of years, pulled by something so massive, so gravitationally powerful, that it dominates the motion of everything in our cosmic neighborhood. We call it the Great Attractor, and we can't see it. Not directly. It's hidden behind the disk of our own galaxy, obscured by billions of stars and vast clouds of dust that block our view. In what we uncover here, please take a moment to like this video and subscribe to the channel. We're trying to see through the Milky Way's densest regions, through what astronomers call the Zone of Avoidance, trying to glimpse what's pulling us. And what we've discovered is both fascinating and unsettling. The Great Attractor isn't just one thing, it's a region of space where matter has concentrated to such a degree that its gravity influences structures across hundreds of millions of light years. We're falling toward it, have been falling toward it since long before Earth existed. We'll continue falling toward it for hundreds of millions of years to come. Tonight, as you drift towards sleep, let me tell you about this invisible hand pulling our galaxy through space. About the detective work required to map something you can't see directly. About what it means to live in a universe where vast cosmic currents carry us along paths we didn't choose and can't resist. This is a story about motion and gravity, about hidden structures and cosmic choreography, about the humbling realization that our galaxy isn't traveling through space randomly, but following a trajectory determined by invisible architecture on the largest scales imaginable. The story begins in the 1970s with a problem. Astronomers were measuring the velocities of galaxies, trying to understand how fast they were moving and in what directions. This was painstaking work. You observe a galaxy. You measure its redshift, the stretching of its light caused by the expansion of the universe. That tells you how fast it's moving away from us due to cosmic expansion. But galaxies also have peculiar velocities, additional motion caused by gravitational interactions with nearby structures. To understand these peculiar velocities, you need to measure not just redshift, but also the galaxy's actual motion through space relative to the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. When astronomers did this carefully, they noticed something strange. Our galaxy wasn't moving the way it should. If cosmic expansion were the only factor, the Milky Way would be moving in a predictable way relative to the cosmic microwave background. But measurements showed we have an additional velocity component. We're moving at about 600 kilometers per second toward a particular region of the sky, in the direction of the constellations Centaurus and Hydra. This wasn't random motion. This was directed motion. Something was pulling us. At first, researchers thought it might be the Virgo cluster, a massive collection of galaxies about 54 million light-years away. The Virgo cluster contains over 1,000 galaxies and has immense gravitational influence. Our galaxy, along with other members of the local group, is indeed being pulled toward Virgo. But calculations showed that Virgo alone couldn't account for the full 600 kilometers per second. We were moving too fast. Something beyond Virgo had to be pulling us. In 1986, a team of astronomers led by Donald Lynden Bell and colleagues published a landmark paper. They analysed the peculiar velocities of hundreds of galaxies and concluded that there must be a massive concentration of matter about 200 million light-years away, pulling not just our galaxy but thousands of others toward it. They called it the Great Attractor. The name was evocative, slightly ominous. It suggested something mysterious and powerful, drawing galaxies inexorably toward it like moths to a flame. The problem was location. The Great Attractor lies in the direction of the Zone of Avoidance, the region of sky where the Milky Way's disk is thickest. When you look toward the galactic plane, you're looking through billions of stars, through vast molecular clouds, through layers of dust that absorb and scatter light. Visible light can't penetrate this obscuration. Galaxies behind the Zone of Avoidance are hidden from view. It's like trying to see through a dense fog or a thick forest. You know something is there, but you can't observe it directly. This was frustrating. Astronomers had discovered something influencing the motion of countless galaxies, something with gravitational effects extending across hundreds of millions of light years, and they couldn't see it. Couldn't point optical telescopes at it and take pictures, couldn't study its structure or measure its mass directly. They were forced to use indirect methods, inferring the Great Attractor's properties from its gravitational effects rather than from direct observation. The first breakthrough came from X-ray astronomy. X-rays can penetrate dust that blocks visible light. By observing in X-rays, astronomers could peer through the zone of avoidance and detect some of the hidden structures. What they found was intriguing. There were indeed galaxy clusters in that direction, massive accumulations of galaxies surrounded by hot gas that emits X-rays. These clusters were part of what was pulling us, but even they didn't seem massive enough to fully explain the 600 km/s motion. The second breakthrough came from infrared astronomy. Infrared light, with longer wavelengths than visible light, also penetrates dust more effectively. Infrared surveys could map galaxies behind the zone of avoidance that were invisible at optical wavelengths. These surveys revealed a complex structure. There wasn't just one cluster. There were multiple clusters, arranged in a vast overdensity of galaxies stretching across the sky. The Great Attractor wasn't a single object but a region, a concentration of mass distributed across tens of millions of light years. One of the most significant structures discovered was the Norma cluster, located almost exactly in the direction of the Great Attractor, about 220 million light-years away. The Norma cluster is massive, containing thousands of galaxies. It's one of the most massive clusters in the nearby universe. Its location and mass made it a prime candidate for being the core of the Great Attractor. But even Norma wasn't enough. The numbers still didn't quite add up. The observed mass, even including Norma and other nearby clusters, seemed insufficient to explain the full gravitational effect. Then, in the 2000s, larger and more comprehensive surveys revealed something even bigger. The Great Attractor, it turns out, is itself part of an even larger structure. Astronomers discovered that our motion toward the Great Attractor is just one component of a much vaster pattern. Multiple galaxy clusters, including Virgo and the Great Attractor region, are all flowing together toward an even more massive concentration of galaxies called the Shapley Supercluster, located about 650 million light-years away in the opposite direction from the Great Attractor in our line of sight. This revelation reframed everything. We're not just being pulled by the Great Attractor, we're part of a cosmic river of galaxies flowing along gravitational channels determined by the distribution of mass on the larger scales. The Great Attractor is a waypoint, a significant concentration of mass along our trajectory, but not the ultimate destination. The full picture is more complex, more hierarchical, with structures nested within structures, each contributing to the overall gravitational field that guides galactic motion. In 2014, astronomers published detailed maps of our cosmic neighbourhood, based on velocity measurements of thousands of galaxies. These maps revealed a structure they named Laniakea, from the Hawaiian words meaning immeasurable heaven. Laniakea is our home supercluster, a vast collection of galaxy clusters spanning 520 million light-years. The Milky Way sits near the edge of Laniakea. The Great Attractor region lies toward the centre, and the whole structure, containing the mass of about 100 quadrillion suns distributed across 100,000 galaxies, flows together gravitationally, defining a coherent dynamical system. Understanding Laniakea and the Great Attractor required piecing together evidence from multiple sources: direct observation where possible, indirect inference where necessary, velocity measurements to track motion, mass estimates to calculate gravitational effects, computer simulations to model how structures this large evolve over cosmic time. The result is a picture of our cosmic environment that would have been unimaginable a century ago. We're not just living in a galaxy. We're living in a galaxy that's part of a group, which is part of a cluster, which is part of a supercluster, which is flowing along gravitational channels determined by the universe's large-scale structure. Let me walk you through what it means to be pulled by something you can't see. Start with gravity. Gravity is the weakest of the four fundamental forces, but it operates over unlimited distances and only attracts, never repels. Every mass in the universe pulls on every other mass. The strength of the pull depends on how much mass and how far away. For small masses or large distances, the pull is negligible. But for large masses or moderate distances, gravity becomes dominant. It's what holds planets in orbit around stars, stars in orbit around galactic centres, galaxies in orbit around each other within clusters, and clusters flowing toward concentrations of even greater mass. The Great Attractor represents one of these concentrations. Imagine a landscape with hills and valleys. Objects naturally roll downhill toward the lowest points. The universe's mass distribution creates a similar landscape, but in 3 dimensions and on cosmic scales. Concentrations of mass create gravitational valleys. Lower density regions create gravitational hills or plateaus. Galaxies move through this landscape like water flowing across terrain, following paths of least resistance, accumulating in the valleys, forming rivers and streams of motion. Our galaxy is in one such stream. We're flowing toward the Great Attractor region because it represents a significant gravitational valley in our cosmic neighbourhood. The motion isn't random. It's determined by the distribution of mass around us. And that distribution isn't static. It's the result of billions of years of gravitational evolution, of matter slowly accumulating in regions that started with slightly higher density in the early universe, of gravitational instability amplifying small differences into large structures. The early universe was remarkably smooth. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang. At that time, matter was distributed almost uniformly. Temperature variations, which correspond to density variations, were about 1 part in 100,000. Tiny ripples in an otherwise smooth sea, but those tiny ripples were seeds. Regions slightly denser than average had slightly stronger gravity. They attracted surrounding matter, growing denser, positive feedback, the rich get richer. Over millions and billions of years, tiny density, differences amplified into galaxies, galaxy clusters, and superclusters. The universe's large-scale structure, including the Great Attractor and Laniakea, is the result of this process. Computer simulations of cosmic structure formation reproduce this evolution remarkably well. You start with initial conditions matching the observed cosmic microwave background. You let gravity operate over billions of years. You watch as dark matter clumps together, forming halos. You watch as normal matter falls into these halos, forming galaxies. You watch as galaxies merge and cluster. You watch as clusters flow together along filaments, creating superclusters. The simulations produce structures strikingly similar to what we observe. The Great Attractor in these simulations is a natural outcome, not inevitable in every detail, but typical, common, expected in a universe governed by gravity and starting from slightly non-uniform initial conditions. Dark matter plays a crucial role. Most of the mass in the universe isn't ordinary matter made of atoms. It's dark matter, something that doesn't emit or absorb light but interacts gravitationally. Dark matter outweighs ordinary matter by about 5 to 1. The gravitational landscape that guides galactic motion is dominated by dark matter. The Great Attractor region contains vast amounts of dark matter, far more than the luminous matter we can detect in galaxies and hot gas. This dark matter, invisible but influential, is the primary source of the gravitational pull we experience. Measuring the Great Attractor's mass is challenging. You can't simply point a telescope at it and count galaxies, because many galaxies are hidden behind the Zone of Avoidance. You can't weigh the dark matter directly because it doesn't emit light. Instead, you infer mass from gravitational effects. You measure how fast galaxies are moving. You calculate how much mass is needed to produce those motions. You use X-ray observations of hot gas in clusters to estimate cluster masses. You combine these methods to build up a picture of the total mass distribution. Current estimates suggest the Great Attractor region contains mass equivalent to tens of thousands of Milky Way-sized galaxies, concentrated in a volume perhaps 50 to 75 million light-years across. That's immense, incomprehensibly massive, and it's pulling us toward it at 600 kilometers per second. Every second, we're 2 million kilometers closer to the Great Attractor than we were the second before. Every day, about 50 billion kilometers closer. Every year, about 18 trillion kilometers. In a million years, we'll have moved about 18 quintillion kilometers toward it. These numbers are too large to grasp intuitively, but they represent real motion through real space, driven by real gravitational forces. Should we be concerned? Are we going to crash into the Great Attractor? No, not even close. While we're moving toward it, the expansion of the universe is also at work. Space itself is expanding, carrying distant galaxies away from us. For very distant objects, this expansion dominates over local gravitational motion. The Great Attractor region is close enough that its gravity influences us, but not close enough that we're on a collision course. We're flowing toward it, but the overall expansion of the universe means we'll never actually reach it. The cosmic choreography is more complex than simple attraction. It's attraction fighting against expansion, with expansion ultimately winning at large enough scales. Think about the timescales involved. We've been moving toward the Great Attractor for billions of years. Earth didn't exist when this motion began. The Sun wasn't born yet. Our galaxy looked different, was positioned differently, but was already part of this cosmic flow. And we'll continue this motion for billions of years into the future. Long after human civilization has ended, assuming we don't spread beyond Earth, long after the Sun has exhausted its fuel and died, the galaxy will still be flowing through the gravitational landscape, following paths determined by mass distributions we're only beginning to map comprehensively. There's something humbling about this realization. We think of ourselves as agents, making choices, determining our paths, and on human scales that's true. We have autonomy, we make decisions, we shape our immediate environment, but zoom out far enough and we're passengers. Our entire solar system is orbiting the galactic center, completing one revolution every 230 million years. Our galaxy is part of the local group, gravitationally bound to Andromeda and other nearby galaxies. The local group is falling toward the Virgo cluster. All of this is flowing toward the Great Attractor region as part of Laniakea, and Laniakea itself is moving relative to even larger structures. We're nested within hierarchies of motion, each determined by gravitational forces operating on scales beyond our individual influence. This doesn't mean our choices don't matter. They matter enormously on human scales, on the scales where we live our lives. But it contextualizes those choices. It reminds us of our place in a much larger system. We're part of the universe, not separate from it. The same forces that govern the motion of galaxies govern the orbits of planets and the falling of apples. Gravity operates across all scales, connecting the cosmic to the personal. The Great Attractor also raises questions about the future. Where are we going? Not just as a species, but as a galaxy, as a supercluster? The answer depends on dark energy, the mysterious force causing the universe's expansion to accelerate. Current observations suggest dark energy dominates cosmic dynamics on the larger scales. Structures like Laniakea are already as large as they'll ever get. They've stopped growing. The expansion of space driven by dark energy is pulling apart the universe, faster than gravity can pull it together on very large scales. This means Laniakea, including the Great Attractor region, will remain gravitationally bound. The galaxies within will continue influencing each other, merging occasionally, orbiting in complex patterns. But Laniakea will become increasingly isolated. Other superclusters are receding from us, carried away by expansion. Eventually, billions of years from now, Laniakea will be alone in an expanding universe, all other superclusters having receded beyond our cosmic horizon. The Great Attractor will continue pulling galaxies toward itself within our supercluster, but there won't be external structures to interact with. We'll be cosmically isolated. This future seems lonely, but it's the consequence of living in an accelerating universe. Dark energy ensures that large-scale structure formation has ended. The cosmic web of filaments and clusters we observe today is the final architecture. It will evolve internally, with galaxies merging and clusters consolidating, but the overall pattern is set. The Great Attractor will remain a dominant gravitational influence within Laniakea indefinitely, shaping the motion of galaxies for trillions of years. Let me describe what the Zone of Avoidance looks like and why it's such an observational challenge. When you look at images of the sky from Earth, the Milky Way appears as a bright band stretching across the sky. This band is our view of the galaxy's disk from inside. We're located in the disk, about 2/3 of the way from the centre to the edge, and when we look toward the galactic plane, we're looking through the disk itself. The density of stars is highest in the disk. The concentration of dust and gas is highest in the disk, and this material blocks light from objects behind it. The Zone of Avoidance is roughly a 20-degree wide band centered on the galactic plane. Within this zone, extinction from dust can be dozens of magnitudes. That means light is dimmed by factors of billions or trillions. A galaxy that would be easily visible above or below the galactic plane becomes completely invisible when viewed through the Zone of Avoidance. Astronomers estimate that about 20% of the sky is obscured by the Zone of Avoidance. 20% of the visible universe, from our perspective, is hidden behind our own galaxy. This includes significant portions of the Great Attractor region. Observing through the Zone of Avoidance requires wavelengths that penetrate dust. X-rays can work, though they are absorbed by Earth's atmosphere and require space-based telescopes. Infrared works better. Longer wavelength infrared in particular passes through dust relatively unimpeded. Radio waves also penetrate dust easily. By combining observations at multiple wavelengths, astronomers can partially pierce the veil and map structures behind the Zone of Avoidance. One of the most productive approaches has been using the 21 centimeter line, the radio wavelength at which neutral hydrogen emits. Galaxies contain neutral hydrogen, and this hydrogen can be detected even through the Zone of Avoidance. Radio surveys mapping neutral hydrogen emission have discovered hundreds of galaxies hidden behind the Milky Way's disk. These discoveries fill in gaps in our understanding of the cosmic web and help refine maps of large-scale structure. The Norma cluster, one of the Great Attractor's main components, was largely unknown until infrared and X-ray observations penetrated the Zone of Avoidance. Once detected, it became clear that Norma is one of the most massive clusters in the nearby universe, comparable to the famous Coma cluster, but largely hidden from view by its unfortunate location behind the galactic plane. Discovering Norma was like finding a major city that had been hidden by a mountain range. It was there all along, influencing its surroundings, but invisible to us until we developed the tools to see through the obscuration. The Great Attractor region contains multiple clusters besides Norma. There's the Centaurus cluster, easier to observe because it's not fully behind the Zone of Avoidance. There are several smaller clusters and groups of galaxies. Altogether, the region contains perhaps dozens of galaxy clusters and thousands of individual galaxies. The total mass, including dark matter, is on the order of 10 to the 16th solar masses. That's 10 quadrillion times the mass of the Sun. It's the kind of number that stops having intuitive meaning. It's just vast, incomprehensibly vast. Galaxies within the Great Attractor region are themselves moving. They're not static. They orbit within clusters. Clusters interact gravitationally. Some galaxies are falling into clusters for the first time. Others have been cluster members for billions of years, orbiting the center, experiencing tidal forces, occasionally merging with neighbors. The region is dynamically active, a gravitational maelstrom where thousands of galaxies interact in complex ways. From outside, though, from our vantage point 200 million light-years away, the Great Attractor region appears relatively simple. It's a concentration of mass. It pulls. We respond. The complexity of its internal dynamics is invisible to us at this distance. We measure its gross properties: location, mass, gravitational influence. The details are lost to distance and obscuration. This is generally true of large-scale structure. From far enough away, complexity simplifies. A galaxy cluster containing thousands of galaxies, each with billions of stars, each star potentially with planets, all of this orbiting and interacting in complicated ways, from sufficient distance reduces to a point of light with measurable mass and velocity. Information is lost. Detail disappears. But the large-scale patterns, the flow of matter along gravitational channels, the accumulation of mass in overdense regions, these become clear. Mapping the universe's large-scale structure is an ongoing project. Surveys like the Sloan Digital Sky Survey have measured positions and velocities of millions of galaxies, revealing the cosmic web in unprecedented detail. Filaments of galaxies stretch across hundreds of millions of light-years, connecting clusters. Voids, regions with few galaxies, occupy large volumes. Clusters and superclusters mark the intersections of filaments, the gravitational nodes where mass accumulates. The Great Attractor and Laniakea are part of this web, one system among many, each contributing to the overall architecture of the universe. Understanding this architecture has profound implications. It tests cosmological theories. The distribution of mass on large scales depends on initial conditions from the early universe, on the properties of dark matter and dark energy, on the rules of gravity and structure formation. By mapping large-scale structure, we're testing fundamental physics. Deviations from predictions would indicate new physics, missing components, incorrect assumptions. So far, Observations match predictions remarkably well. The universe behaves as expected from our theories. The Great Attractor exists where such structures should exist. Its properties match expectations. This is reassuring but also slightly disappointing. Discoveries that confirm existing theories are satisfying but less exciting than surprises that require new physics. There's also a philosophical dimension to thinking about the Great Attractor. We're being pulled towards something. Does this have meaning? Purpose? No, not in any intentional sense. The Great Attractor isn't pulling us for a reason. It's pulling us because it has mass, and mass creates gravitational fields, and gravitational fields accelerate objects toward the source. It's physics. Causation without intent, mechanism without purpose. This can feel cold, impersonal. We live in a universe governed by mathematical laws that don't care about us, that operate with complete indifference to human concerns or meanings. But there's also beauty in this. The same laws that pull us toward the Great Attractor hold Earth in orbit around the Sun, preventing us from flying off into space. The same gravity that operates on cosmic scales enables stars to form, planets to coalesce, life to emerge on stable worlds. Gravity, for all its impersonality, creates the conditions for everything we care about. The Great Attractor is gravity writ large, operating on scales that humble us, reminding us of how vast the universe is, how small our place within it, but also how thoroughly integrated we are into cosmic processes. We're made of atoms forged in stars. Those stars formed in galaxies. Those galaxies are part of clusters. Those clusters flow along gravitational channels shaped by the universe's large-scale structure. We're connected, through layers of hierarchy, to the cosmic web. The Great Attractor pulling our galaxy is, in a very distant sense, pulling us. Every atom in your body is part of the Milky Way's motion toward the Great Attractor region. You're participating in cosmic dynamics simply by existing, by being made of matter subject to gravity. This connection, though physically tenuous, is conceptually profound. You're not separate from the cosmos, you're an integral part of it. As you drift towards sleep, think about motion. You're lying still, or nearly still, relative to Earth's surface, but Earth is rotating, completing one revolution every 24 hours, carrying you eastward at hundreds of kilometers per hour depending on your latitude. Earth is orbiting the Sun at 30 kilometers per second, completing one orbit per year. The Sun is orbiting the galactic center at 220 kilometers per second, taking 230 million years to complete one orbit. The galaxy is moving toward the Great Attractor at 600 kilometers per second as part of the Laniakea supercluster's internal dynamics. And Laniakea itself is moving relative to the cosmic microwave background frame, the closest thing we have to an absolute reference frame in cosmology. Add all these motions together and you're moving at over 1,000 kilometers per second through space in various directions simultaneously. Yet you feel still. The motions are so smooth, so constant that you don't perceive them. This is the principle of relativity. Motion at constant velocity is indistinguishable from rest. You can only detect acceleration, changes in motion. And while we're accelerating toward the Great Attractor, the acceleration is tiny, spread over cosmic distances and times. You'll never feel it. No human will ever feel it. But it's real, it's measurable, it's shaping the destiny of our galaxy. The Great Attractor will never be seen clearly. It will always be partially hidden behind the Zone of Avoidance. Future telescopes will improve our view. We'll map more galaxies, detect more clusters, refine our understanding of the mass distribution. But we'll never have an unobstructed view the way we do of structures above or below the galactic plane. This limitation is permanent, a consequence of where we happen to be located within our galaxy. Other civilizations, if they exist, in galaxies positioned differently, might have clear views of what we struggle to see. They might find other structures hidden from their view but visible to us. The universe's appearance depends on where you observe from. There's no privileged vantage point. Every location has its advantages and blind spots. This is humbling too. We're not at the center. We're not in a special location. We're in a fairly typical spiral galaxy, in a fairly typical part of a fairly typical supercluster. The structures we struggle to see aren't inaccessible because they're fundamentally obscure, but because of the accident of our location. Change our position, and everything changes. But we can't change our position on cosmic scales. We're here. We work. With what we have. We use clever techniques to peer around obstacles. We infer what we can't see directly. We build models and test them. We gradually improve our understanding despite limitations. The Great Attractor represents a milestone in this process. When first proposed in the 1980s, it was controversial. Some astronomers doubted its existence. They suggested the observed motions might be measurement errors or caused by something else. But as more data accumulated, as more galaxies were measured, as structures behind the Zone of Avoidance were gradually revealed, the evidence became overwhelming. The Great Attractor is real. Its gravitational influence is real. Our motion toward it is real. What started as a hypothesis based on puzzling observations became established fact, woven into our understanding of cosmic structure. This is how science progresses. Observations lead to hypotheses. Hypotheses make predictions. More observations test predictions. Over time, successful hypotheses become accepted theories. The process is gradual, consensus builds slowly, but it's reliable. The scientific method, for all its limitations and human flaws in implementation, produces knowledge that's increasingly accurate and comprehensive. The Great Attractor, once speculative, is now part of the established picture of our cosmic neighbourhood. Future discoveries might refine details, might reveal additional complexity, but the basic fact of its existence and influence is secure. What will we learn next about the Great Attractor? Ongoing surveys continue mapping galaxies and measuring velocities. Each new measurement slightly refines our understanding. New telescopes, particularly in infrared and radio, will penetrate the Zone of Avoidance more effectively. We'll discover more hidden galaxies. We'll map the structure more completely. We'll measure masses more accurately. We'll understand the relationship between the Great Attractor region and surrounding structures more clearly. We'll trace the flow of matter through Laniakea with better precision. But we'll also recognize the limits of what's knowable. The Great Attractor region is 200 million light-years away. Light from that region takes 200 million years to reach us. We see it as it was in the distant past, when dinosaurs were beginning to dominate Earth. What's happening there now, we won't know for 200 million years. The information hasn't reached us yet. This light speed delay is fundamental. It's not a technological limitation we can overcome. It's built into the structure of space-time. The universe has a speed limit, and information can't travel faster than light. So we're always viewing distant structures as they were, not as they are. Moreover, many of the interesting dynamics occur on timescales of billions of years. Galaxies merge over hundreds of millions or billions of years. Clusters evolve over similar timescales. We observe these processes frozen at single moments. We see snapshots, not movies. To understand evolution, we compare many structures at different stages, inferring the progression from statistical analysis rather than watching individual systems change. It's like understanding human aging by looking at photographs of many different people at different ages rather than watching one person age. You can learn the general pattern, but you miss the individual variation and contingency. The Great Attractor will continue influencing our galaxy for billions of years, long after human civilization, long after Earth becomes uninhabitable, long after the Sun dies. The galaxy will still be responding to the gravitational landscape, still flowing along paths determined by mass distributions. This continuity, this persistence of cosmic processes across timescales that dwarf human history, is both comforting and alienating. Comforting because it speaks to stability, to underlying order. Alienating because it reminds us how brief our existence is compared to cosmic timescales. But brief doesn't mean meaningless. Ephemeral doesn't imply insignificant. We exist in this moment, in this location, with the capabilities to observe and understand the cosmos. That's remarkable. It might be rare. Intelligence, consciousness, the drive to understand, these might be uncommon in the universe. If they are, then our brief moment matters enormously. We're the universe's way of knowing itself, at least in this corner of space-time. The Great Attractor pulls galaxies, but it doesn't know it's pulling them. We know. We've measured. We've calculated. We've understood. That knowledge is valuable regardless of timescale or cosmic indifference. Close your eyes now. Let your breathing slow. Feel the stillness of your body relative to the bed, the room, the building. But know that you're moving. The Earth carries you through space, that the Sun carries Earth, that the galaxy carries the Sun, that cosmic flows carry the galaxy, that you're part of vast motions you don't perceive, but that are real and measurable and ongoing. You're nested within hierarchies of motion, each determined by gravity's pull, each contributing to the cosmic dance of matter through space and time. The Great Attractor pulls us, 600 kilometers every second, 2 million kilometers every hour, 50 billion kilometers every day. Incomprehensible distances accumulated over incomprehensible times. We've been moving this way for billions of years. We'll continue moving this way for billions more. The motion is real but imperceptible, significant but invisible, determined by forces beyond our control, operating on scales beyond our direct influence. And that's okay. That's how the universe works. We're passengers on a cosmic journey, participants in dynamics we're only beginning to fully understand. Rest now. Dream of galaxies flowing through space, following gravitational rivers toward unseen destinations. Dream of the Great Attractor, massive and hidden, shaping the motion of thousands of galaxies across hundreds of millions of light years. Dream of Laniakea, our home supercluster, the immeasurable heaven containing everything we can ever hope to reach, flowing together in gravitational harmony. Dream of the cosmic web, filaments and voids stretching across billions of light years, the universe's architecture revealed through patient observation and careful analysis. You're part of this, not just intellectually, but physically. The same matter, the same forces, the same dynamics. You're connected to the cosmos in ways both profound and mundane, connected by gravity, by atomic composition, by evolutionary history stretching back to the Big Bang. The Great Attractor pulls you, however indirectly, however slightly. You're responding, however imperceptibly. You're participating in cosmic motion simply by being matter in a gravitating universe. Sleep well, traveller. The journey continues whether you're awake or asleep. The Great Attractor remains, hidden but influential, pulling us and countless others toward a gravitational rendezvous that will take hundreds of millions of years to complete, and that will never truly arrive, because expansion wins at the larger scales, because the universe is stranger and more complex than simple attraction. But the pull is real, the motion is real, and we're privileged to live in an era when we can measure it, understand it, contextualize it within the grander story of cosmic evolution. Let me take you deeper into what we've learned about the Great Attractor and the cosmic flows it generates. Because the story doesn't end with discovery. The story expands with every new measurement, every new survey, every refinement in our understanding of how matter moves on the larger scales. The Great Attractor is part of a story about structure, about how the universe organized itself from near-perfect smoothness into the complex web of galaxies we observe today. Understanding this organization means understanding our place within it, our motion through it, our ultimate fate within cosmic currents we can measure but cannot control. When astronomers first calculated that we were moving at 600 kilometers per second toward a specific region of sky, the immediate question was, why? What's special about that direction? The universe is supposed to be isotropic, the same in all directions on large scales. If that's true, there shouldn't be preferred directions of motion. Our galaxy should be participating in cosmic expansion relatively uniformly, with only small deviations caused by local gravitational interactions. But 600 kilometers per second isn't a small deviation. It's substantial. It requires substantial mass to cause it. So the search began for that mass. The Virgo cluster was the first candidate. Virgo is impossible to miss if you're surveying nearby galaxies. It contains over 1,000 galaxies within a volume of about 15 million light-years across. Its total mass is roughly 10 to the 15th solar masses, a quadrillion suns worth of matter. That's enough to gravitationally influence everything within 100 million light-years. Our local group, containing the Milky Way and Andromeda and dozens of smaller galaxies, is definitely being pulled toward Virgo. But calculations showed that Virgo alone couldn't account for our full velocity. We were moving too fast. This implied something beyond Virgo, something farther away but more massive, something capable of pulling not just our local group but Virgo itself, along with thousands of other galaxies across vast distances. The geometry of the motion, the direction we were heading, pointed toward a region beyond Virgo, roughly in the direction of the constellations Centaurus and Hydra. And that region, frustratingly, lies behind the Zone of Avoidance, the galactic plane where dust and stars block our view. The zone of avoidance isn't a complete barrier, it's more like a fog. Some light gets through, but it's dimmed and reddened by scattering. Dust grains, tiny particles of carbon and silicon compounds, absorb blue light more efficiently than red light. This means objects viewed through dust appear redder than they actually are, a phenomenon called reddening. Astronomers can correct for this effect if they know how much dust is present, but the corrections become uncertain for thick obscuration. And in the zone of avoidance, the obscuration is very thick indeed. Early attempts to peer through the zone used optical telescopes with filters that isolated red light, where extinction is somewhat less severe. These surveys found some galaxies, but they were faint, difficult to study, and their distances were hard to determine. You need clear spectroscopy to measure redshift and calculate distance, but spectroscopy requires even more light than simple imaging. For heavily obscured galaxies, getting good spectra was nearly impossible with 1980s technology. The breakthrough came with infrared surveys in the 1990s and 2000s. Infrared light has longer wavelengths than visible light, and dust that blocks visible light is transparent at infrared wavelengths. The 2-micron all-sky survey, or 2MASS, mapped the entire sky in near-infrared light, detecting millions of galaxies, including many behind the zone of avoidance. These observations finally revealed what was hidden. There were indeed massive galaxy clusters in the direction of the Great Attractor. Multiple clusters, in fact, forming a concentration of galaxies that partially explained the observed motion. The Norma cluster emerged as a particularly significant structure. Located about 220 million light-years away, almost directly behind the galactic plane, Norma contains thousands of galaxies in a volume perhaps 10 million light-years across. Its total mass rivals the Coma cluster, one of the largest known galaxy clusters. But while Coma has been studied extensively because it's visible in clear sky, Norma remained largely unknown until infrared surveys revealed it. This asymmetry in knowledge, caused purely by the accident of where we're located in our galaxy, reminds us how observation affects understanding. We study what we can see, what we can't see remains mysterious longer. Alongside Norma, other structures were identified. The Centaurus cluster lies partially outside the zone of avoidance and has been known longer. It's also part of the Great Attractor region. Several smaller clusters and galaxy groups populate the area. Altogether, these structures contain mass estimated at 10 to the 16 solar masses, 10 quadrillion suns, distributed across a region roughly 50 to 100 million light-years in extent. That's sufficient mass to explain much, though not all, of the observed motion toward the region. The remaining mystery was resolved when larger surveys revealed that the Great Attractor is itself part of a flow toward an even larger structure. The Shapley Supercluster, located about 650 million light-years away, but offset from the Great Attractor's direction, contains dozens of rich galaxy clusters with combined mass perhaps 10 times greater than the Great Attractor region. Shapley is one of the most massive structures in the nearby universe, and its gravitational influence extends across enormous volumes. Computer models show that both the Great Attractor region and structures like Virgo are being pulled toward Shapley. We're not falling toward the Great Attractor alone. We're part of a larger flow that includes the Great Attractor. This revelation required rethinking the cosmic geography. The motion we observe isn't toward a single point, but along a vector that reflects multiple gravitational sources. The Great Attractor represents a significant waypoint, a concentration of mass that dominates local dynamics. But the ultimate destination, if such a concept makes sense, is the Shapley concentration. However, even this picture is incomplete because cosmic expansion complicates everything. We're being pulled gravitationally toward these mass concentrations, but space itself is expanding, carrying distant structures away from us. The combination of gravitational attraction and cosmic expansion determines actual trajectories. For the Great Attractor region, which is relatively nearby at 200 million light-years, gravitational effects dominate over expansion. We're genuinely moving toward it through space, not just seeing it recede more slowly than more distant objects, but for Shapley, 650 million light-years away, expansion becomes more significant. We're being pulled toward Shapley, but expansion is also carrying Shapley away from us. The net result is complex motion that requires sophisticated models to predict accurately. Understanding these flows required measuring the velocities of thousands of galaxies This is painstaking work. For each galaxy, you need to measure its redshift, which tells you its recession velocity due to cosmic expansion, plus any peculiar velocity from gravitational effects. Then you need to separate these components. The recession velocity depends on distance, so if you know the distance independently, you can calculate what the recession velocity should be and subtract it from the observed redshift to get the peculiar velocity. But measuring distances independently is challenging. You need standard candles, objects with known intrinsic brightness that allow distance calculation from observed brightness. Or you need other distance indicators like surface brightness fluctuations, or the Tully-Fisher relation linking galaxy rotation speed to luminosity. Once you have peculiar velocities for many galaxies, you can map the flow patterns. Regions where galaxies are moving toward each other indicate overdensities, concentrations of mass. Regions where galaxies are moving apart indicate underdensities, voids. The Great Attractor shows up as a convergence point in these flow maps, a place where velocity vectors from many directions point toward. It's a gravitational sink pulling in surrounding material. The Laniakea Supercluster, mapped in 2014 by Brent Tully and colleagues, represents the culmination of this work. Laniakea is defined by its watershed, the region of space where all matter flows toward a common basin of attraction. Just as water on Earth flows downhill toward rivers and oceans defining drainage basins, matter in space flows toward gravitational attractors, defining gravitational basins. Laniakea is our basin. It spans 520 million light-years and contains about 100,000 large galaxies with total mass around 10 to the 17 solar masses, 100 quadrillion suns. The Great Attractor region lies near Laniakea's centre. We, in the Milky Way, are near the edge. Our motion toward the Great Attractor is motion toward Laniakea's centre, following the gravitational gradient. But Laniakea isn't isolated. It's bordered by other superclusters, Perseus Pisces in one direction, Coma in another, Shapley farther away. These structures are also defined by their watersheds, their internal flows. The boundaries between superclusters are regions where flow patterns diverge, where galaxies on one side flow toward one attractor and galaxies on the other side flow toward another. This watershed definition of superclusters is more physically meaningful than older definitions based on spatial proximity alone. Previously, superclusters were defined as regions of space with higher than average galaxy density. But density alone doesn't tell you about dynamics, about how structures interact gravitationally. The watershed definition captures dynamics. It shows which galaxies are gravitationally bound together, which will interact and potentially merge over cosmic timescales, which share a common evolutionary future. Laniakea's galaxies are family in a dynamical sense, flowing together, responding to the same gravitational landscape. Mapping Laniakea required measuring peculiar velocities for thousands of galaxies. The Cosmic Flows project, led by Tully's team, compiled data from multiple sources: Tully-Fisher distances, surface brightness fluctuations, type wire supernovae, and other methods. Each distance measurement combined with redshift yields a peculiar velocity. Thousands of these measurements, combined statistically and smoothed to reduce noise, produce a velocity field. From the velocity field you can trace flow lines, identify attractors, define watersheds. The result is a map of our cosmic neighbourhood's dynamics, showing not just where galaxies are but where they're going. This map reveals several important features. First, Laniakea is flatter than a sphere, more like a stretched sheet or filament. This reflects the universe's large-scale structure, which organises into filaments and walls surrounding voids. Second, the Great Attractor region lies in the high-density core of Laniakea, where multiple filaments intersect. This geometry explains why it's such a strong attractor. It's fed by streams of galaxies flowing along filaments from multiple directions. Third, our position near Laniakea's edge means we're moving both toward the Great Attractor and somewhat toward Shapley beyond Laniakea's boundary. Our velocity vector points through Laniakea toward the next structure over. Fourth, and perhaps most humbling, Laniakea is one of countless similar structures in the observable universe. There's nothing special about it except that we happen to live in it. Other observers in other superclusters would map their own Laniakeas, their own Great Attractors, their own flow patterns. The universe repeats these patterns across enormous scales. Structure is hierarchical: galaxies in groups, groups in clusters, clusters in superclusters, superclusters in even larger structures like walls and filaments. The Great Attractor operates at the supercluster level, but similar dynamics occur at every level of hierarchy. This hierarchical organization emerged naturally from gravitational instability operating over billions of years. The early universe, as revealed by the cosmic microwave background, was smooth to about 1 part in 100,000. Density variations were tiny, but gravity amplifies variations. A region slightly denser than average has slightly stronger gravity, attracting nearby matter, becoming even denser, attracting even more matter. Positive feedback. Over millions of years, small density enhancements grew into the first structures, dark matter halos that later seeded galaxy formation. Over hundreds of millions of years, these halos merged and grew into galaxy clusters. Over billions of years, clusters organized into superclusters. The Great Attractor region represents this process operating at large scales, matter collecting in a region that was slightly overdense billions of years ago. Dark matter plays the crucial role in this process. Normal matter, the atoms that make up stars and planets and us, represents only about 15% of total matter. The other 85% is dark matter, something that interacts gravitationally but not electromagnetically. It doesn't emit, absorb or scatter light. It's invisible except through its gravitational effects, but those effects dominate structure formation. Dark matter clumped first, forming halos that then attracted normal matter. Galaxies formed within dark matter halos. Clusters are dominated by dark matter. The Great Attractor region's mass is mostly dark matter, perhaps 90% or more. The galaxies we see are traces of the underlying dark matter distribution, bright markers of a much larger invisible structure. Estimating the dark matter distribution requires combining multiple observations. Galaxy surveys show where luminous matter is concentrated. X-ray observations reveal hot gas in clusters. This gas is held in place by gravity, so its temperature and distribution constrain the gravitational potential, which depends on total mass including dark matter. Gravitational lensing, the bending of light by mass, provides another mass probe. Light from distant galaxies is bent passing through foreground structures. The amount of bending depends on the mass distribution of the lens. Detailed lensing studies of galaxy clusters reveal their mass profiles, showing that dark matter extends well beyond the visible galaxies, forming massive halos. For the Great Attractor region, all these methods indicate enormous dark matter concentrations. The visible galaxies, the X-ray emitting gas, these are just the tips of icebergs. Most of the mass is dark matter, forming vast halos that dominate the gravitational landscape. Our motion toward the Great Attractor is motion toward this invisible mass. We're pulled by something we can't see directly, something we infer from its effects. This is both frustrating and scientifically fascinating. Frustrating because we'd like to observe dark matter directly, to understand what it is, to study its properties beyond its gravitational influence. Fascinating because it demonstrates how much of the universe remains mysterious, how much we've learned by being clever with indirect methods. The nature of dark matter remains unknown. It's not normal atoms. We know that from multiple lines of evidence. The most popular hypothesis is that dark matter consists of weakly interacting massive particles, or WIMPs, subatomic particles produced in the early universe that rarely interact with normal matter except gravitationally. Experiments deep underground search for rare dark matter particle collisions with atomic nuclei. Particle colliders try to create dark matter particles in high-energy collisions. Space-based telescopes look for signals from dark matter particles annihilating each other. So far, direct detection has proven elusive. Dark matter remains stubbornly invisible at all wavelengths, and to all detection methods except gravity. Alternative theories propose modifications to gravity rather than new particles. Perhaps gravity behaves differently on very large scales than we think, producing effects we attribute to dark matter without actually requiring dark matter's existence. These modified gravity theories make predictions that can be tested observationally. So far, observations favour dark matter over modified gravity, but the question isn't fully settled. The Great Attractor and its gravitational effects are evidence for something beyond visible matter, whether that's dark matter particles or modified gravity dynamics. Regardless of dark matter's nature, its effects are clear. The Great Attractor region has mass far exceeding what we see in galaxies and gas. That mass creates a gravitational field extending across hundreds of millions of light years. That field determines the motion of galaxies, including ours. We're responding to dark matter, whatever it is, flowing along gradients in its distribution, falling down gravitational wells created by its accumulation in overdense regions. This raises a question. Will we ever reach the Great Attractor? Will our galaxy eventually collide with galaxies in that region, merging in some future gravitational interaction? The answer is complicated by cosmic expansion. If the universe weren't expanding, then yes, gravitational attraction would eventually pull everything together. Galaxies would fall toward attractors, merging over timescales of billions or tens of billions of years. Eventually, everything gravitationally connected would coalesce into one enormous structure. But the universe is expanding, and not just expanding, but accelerating. Dark energy, the mysterious component causing acceleration, opposes gravitational collapse on the very largest scales. For structures like Laniakea, currently about 520 million light-years across, internal gravitational forces are strong enough to hold things together against expansion. Laniakea won't expand apart, it's gravitationally bound. Galaxies within Laniakea will continue interacting, orbiting, occasionally merging. Over tens of billions of years, Laniakea's galaxies might merge into a smaller number of larger galaxies, but they'll remain within the same bound structure. However, structures beyond Laniakea are receding due to cosmic expansion. Shapley, though gravitationally influencing us, is also being carried away by expansion. Other nearby superclusters are receding. Eventually, billions of years from now, Laniakea will be isolated. The galaxies in Laniakea will be all we can see. Everything else will have receded beyond our cosmic horizon, carried away by expansion faster than light can travel from them to us. This isolation is the fate of gravitationally bound structures in an accelerating universe. The largest structures that exist now are the largest that will ever exist. The era of structure formation has ended on the very largest scales. Within Laniakea, though, dynamics will continue. The Great Attractor will keep pulling galaxies toward itself. Some will fall in, joining the concentration. Others will orbit at larger distances, never quite reaching the center. The Milky Way's trajectory depends on multiple factors. Our current velocity, our distance from the Great Attractor, their mass distribution of intervening structures, the details of Laniakea's gravitational field. Current models suggest we'll pass relatively close to the Great Attractor region, on timescales of billions of years, perhaps approaching within tens of millions of light-years at closest approach. Whether we merge with any Great Attractor galaxies directly is uncertain and depends sensitively on initial conditions we don't know precisely. Adding complexity is the Milky Way's impending collision with Andromeda. In about 4 billion years, our two galaxies will begin merging. This merger will dramatically alter our trajectory. The combined Milky Way-Andromeda system, sometimes called Milkomeda, will have different mass, different angular momentum, different velocity than the Milky Way alone. Milkomeda's trajectory through Laniakea's gravitational field will differ from the Milky Way's current trajectory. Predicting exactly where Milkomeda will go requires simulating both the merger and the subsequent evolution in Laniakea's time-varying gravitational field. Such simulations are computationally intensive and depend on assumptions about dark matter distribution and other factors. What we can say confidently is that Milkomeda will remain within Laniakea. The binding energy is sufficient. We're not escaping into intergalactic space. We're bound to this supercluster, destined to interact gravitationally with its other members indefinitely. The Great Attractor will continue influencing us, perhaps more strongly as we approach it, or less strongly if our orbit carries us away temporarily before returning. The long-term behavior is orbital and chaotic in the mathematical sense, with outcomes sensitive to initial conditions and difficult to predict precisely over timescales of billions of years. Think about what this means experientially. If humanity survives for billions of years, if our descendants spread beyond Earth and establish civilizations across the galaxy, and eventually across other galaxies, they'll witness the unfolding of these cosmic dynamics. They'll see the Milky Way Andromeda merger up close, watching as the two galaxies collide, spiral around each other, eventually coalescing. They'll see the resulting disturbances, star formation triggered by gas collisions, stellar orbits perturbed into new configurations, possibly some stars ejected into intergalactic space. They'll track Milkomeda's motion toward the Great Attractor region, watching distances shrink over millions and billions of years. Eventually, perhaps, they'll visit the Great Attractor galaxies. If we develop interstellar travel capability and sustain it long enough, we could travel those 200 million light years. Not quickly, not with any currently imaginable technology, but over timescales of millions of years such journeys become conceivable. Imagine learning about the Great Attractor from Earth, observing it through obscuration, measuring its gravitational effects, and then, millions of years later, having descendants actually travel there, seeing those galaxies up close, studying them directly, confirming or revising everything we inferred from distant observations. This multi-generational, multi-million-year perspective is hard to adopt from our human vantage point of decades-long lifespans. But it's relevant for thinking about cosmic evolution. The Great Attractor isn't going anywhere quickly. It's a long-term feature of our cosmic environment, something that will influence our galaxy's trajectory for timescales vastly longer than human history so far. Understanding it means thinking about futures almost incomprehensibly distant. Timescales where Earth itself might be long gone, but our galaxy continues its journey through Laniakia's gravitational landscape. The Great Attractor also connects to cosmological questions about the fate of the universe. Current evidence suggests the universe will expand forever, accelerating continuously under dark energy's influence. Galaxies not already gravitationally bound will recede beyond each other's horizons. Gravitationally bound structures like Laniakea will remain bound but isolated. Eventually, trillions of years from now, star formation will cease, as gas is exhausted. Existing stars will age and die. Galaxies will darken. The universe will enter what's sometimes called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, black holes. These remnants will continue orbiting, responding to gravity, including the gravity of the Great Attractor region, but in darkness and cold. Even further in the future, quantum mechanical processes might cause protons to decay, disintegrating even the stellar remnants. Black holes will evaporate through Hawking radiation, taking unimaginable timescales but eventually vanishing. The universe will approach maximum entropy, heat death, a state where no gradients exist, no energy flows, nothing happens. But before then, for trillions upon trillions of years, the gravitational architecture established now, including the Great Attractor and Laniakea, will persist and govern the motion of matter. The Great Attractor will be pulling galaxies toward itself long after the last stars have died. These far future scenarios are speculative, based on extrapolations of current understanding. Dark energy's properties might change. New physics might emerge at long timescales. We don't know with certainty what will happen trillions of years from now, but barring surprises, the gravitational structures we observe today represent long-lived features of cosmic architecture. The Great Attractor isn't temporary, it's a permanent fixture, at least on timescales approaching the universe's current age. There's a melancholy beauty in this persistence. The same structures pulling us now will continue pulling remnants of our galaxy far into the future, long after everything we care about has ended. Gravity is patient. Gravity is eternal on cosmic scales. The Great Attractor will keep attracting until there's nothing left to attract, until proton decay or black hole evaporation erases even the substrates of matter. And even then, the space-time curvature, the gravitational field itself will persist until the universe's final state. But that's far in the future, incomprehensibly far. For now, on human timescales and even on galactic timescales of billions of years, the Great Attractor is dynamic, influential, shaping the cosmic environment we inhabit. Understanding it helps us understand our place in the universe's structure, helps us appreciate the scales on which gravity operates, helps us recognize that motion and change characterize the cosmos at every level. Let's return to something more immediate, the observation problem. The Zone of Avoidance will always limit our view of the Great Attractor region. Future telescopes will improve penetration, revealing more hidden galaxies, but the fundamental obscuration remains. We can't relocate Earth to get a better view. We're stuck with the perspective we have. This teaches an important lesson about science and knowledge. Observation is contingent. What we know depends on where and when we observe from. Other locations, other times would yield different data, perhaps revealing what's hidden to us while hiding what we can see. If intelligent civilizations exist elsewhere, their astronomical knowledge reflects their observational circumstances. A civilization in a galaxy oriented differently viewing the Great Attractor region without obscuration, would have known about it earlier and in more detail than we did. They'd see clearly what we struggle to perceive, but they'd have their own blind spots, regions hidden by their galaxy's dust, structures we can see that they cannot. No single observer has perfect information. Every perspective is partial. This epistemological point applies broadly. Our knowledge is always situated, always limited by our instruments and locations and capabilities. We work with what we have. We develop clever techniques to overcome limitations. Infrared astronomy to peer through dust. Radio observations to detect neutral hydrogen. Velocity measurements to infer mass distributions gravitationally. We build models and test them. We gradually improve our understanding despite unavoidable constraints. The Great Attractor's discovery and characterization exemplifies this process, starting from puzzling observations, inferring hidden structures, gradually revealing them through multi-wavelength campaigns, refining models as data improves. The process isn't finished. Ongoing surveys continue measuring galaxy velocities. New infrared telescopes map the Zone of Avoidance in greater detail. Future missions might provide even better data. Each improvement refines our picture of the Great Attractor, of Laniakea, of the cosmic web. The work is incremental. Progress is gradual. But it's real progress, expanding human knowledge, pushing back the boundaries of ignorance, revealing the universe's structure more clearly with each passing year. And there's something deeply satisfying about this work, about pointing telescopes at obscured regions of sky, patiently gathering faint signals, processing data meticulously, extracting information about distant structures, about measuring velocities one galaxy at a time, accumulating thousands of measurements, combining them statistically to map large-scale flows, about building theoretical models that reproduce observations, testing them against new data, refining them when discrepancies appear. This is science at its best, patient, collaborative, self-correcting, gradually converging on truth. The Great Attractor will never be as iconic as some other astronomical objects. It doesn't have the visual impact of a nebula or galaxy. It doesn't have the exotic strangeness of a black hole or neutron star. It's hidden, diffuse, its influence felt rather than seen, but its significance is profound. It dominates the gravitational environment of our cosmic neighborhood. It shapes the motion of thousands of galaxies, including ours. It exemplifies how matter organizes on the larger scales. Understanding it means understanding cosmic structure formation, understanding dark matter's role, understanding the universe's evolution from smooth early conditions to today's complex web of galaxies, clusters, and superclusters. As you approach sleep, let your mind rest with this knowledge. You're moving through space, carried by Earth's rotation and orbit, carried by the Sun's orbit around the galactic center, carried by the galaxy's motion toward the Great Attractor as part of Laniakea's internal flows. These motions are real but imperceptible, constant but unnoticed. They operate on scales far beyond human perception. You'll never feel the 600 kilometers per second velocity toward the Great Attractor. No human will. But it's real. It's measurable. It's part of your existence as physical being in a gravitating universe. Rest in this motion, in the knowledge that cosmic forces beyond our control have been guiding our galaxy's path for billions of years and will continue for billions more. In the understanding that we're nested within hierarchies of structure and motion, from the local to the cosmic. In the awareness that science has revealed these structures, has mapped our cosmic neighborhood, has measured the invisible currents carrying us through space. In the appreciation that we live in an era where such knowledge is possible, where instruments and intellect combine to unveil the universe's architecture. The Great Attractor pulls, we respond. This has been true since long before humans existed, and will remain true long after we're gone. The motion is part of cosmic evolution, part of how the universe organized itself from initial smoothness into the complex structured cosmos we observe. We're privileged to understand this, to measure it, to contextualize our galaxy's journey within the larger story of structure and motion spanning billions of light years and billions of years. Sleep now, dream of cosmic flows, of galaxies streaming through space like rivers through landscapes following gravitational gradients toward unseen destinations. Dream of the Great Attractor, massive and hidden, shaping the motion of countless galaxies across unimaginable distances. Dream of Laniakea, the immeasurable heaven containing our cosmic home, flowing together in gravitational symphony. Dream of the universe's vast architecture, revealed through human curiosity and persistence, mapped despite obscuration and difficulty, understood despite complexity. You're part of this, part of the motion, part of the structure, part of the universe knowing itself. Rest well, cosmic traveller. The journey continues, the Great Attractor calls, and we answer. Always falling, always flowing, always following the invisible hand of gravity across distances and timescales that humble us even as we measure and comprehend them. The universe is vast, we're small. But we notice, we understand, and that noticing, that understanding might be the most remarkable thing of all.